So we'll just call this optimization. This is 5.4, just part 1. So these are the 6 steps. Yeah. Understand the problem, what you're trying to maximize or minimize. Write a function. And like I said, you'll end up having 2 different equations, and you'll substitute one into the other each time on these. So expect to have 2 different equations. And then you're going to graph the equation and find a reasonable domain. In some cases, you can graph it by hand without a calculator. In other cases, you'll maybe need a calculator to graph it and see what it looks like. And then find where the derivative is 0 or does not exist, and look at the endpoints. So those are all the candidates for an absolute max or absolute min will be where the derivative is 0, does not exist, or at the endpoint. And then find the absolute max or min using the first or second derivative test. As I said, I use the second derivative test when the function is a polynomial function. If it has square roots in it or rational functions, use the first derivative test to avoid doing a second derivative with those. And then ask the question, does your answer make sense? We're going to be banking on your geometry understanding a lot of these. So we'll give you the, in a lot of these they give you the equations as they get more difficult. When they start talking about maximizing the volume of a cylinder for a given surface area, they'll give you this one. So you have to have them memorized, or they'll be in the context of the problem. So here's example 1. It says, what is the largest area possible for a rectangle whose perimeter is 8 meters? So we're basically it's telling us we have 8 meters of fencing. What do the dimensions have to be to maximize the area? So 8 meters of fencing. What dimensions do you need to maximize the area? And yes, it does make a difference. We studied this a little bit in geometry. So there will be 2 equations involved. One is this perimeter equation. Perimeter equals twice x plus twice L. And the other equation that we're going to write here and then do the calculus on is the area equation. But I need my area equation in terms of just one variable x. Okay. That's why we need the 2 equations. So maybe draw the picture here. Write down your perimeter equation, P equals 2x plus 2L. And if area is equal to base times height, and I know the height of this is x, I need to get an equation for the length L. Base times height, or in this case it looks like we've got width times length, so we've got x times L, if you will. I used a capital L. So we'll take this perimeter equation, put 8 in for P. So 8 is equal to 2x plus 2L. Go ahead and solve that for L. Subtract the 2x over. And then divide by 2. So L equals 4 minus x. And so we can label this 4 minus x. And this process, you'll see the same types of problems over and over again. You'll be able to do that even in your head. You'll have labels for the length and the width in terms of one variable. You'll end up doing this with triangles as well, and with some circles, and then also with 3-dimensional prisms and cubes. So those are the dimensions, 4 minus x. So however you want to do it in terms of getting your dimensions in terms of one variable, so that you can have an explicit equation for area here. Area equals base is 4 minus x times the height is x. And that is just a simple 4x minus x squared polynomial function. Okay, they're super easy to work with. All right, what would you say is the domain, a reasonable domain for this? I think we can do this without even graphing it. This is a parabola that would be facing downward. what's the minimum value x could be non-inclusive? 0. Right? Minimum would be right, non-inclusive. So 0, and then it's going to go up to 4. Why do you say 4?
The length would be 0.
Yeah, so if you plugged in 4, the length would be 0, and you'd have no area. So it's between 0 and 4. That's pretty common for these. So domain is between 0 and 4. That's cool. This is what kind of function in terms of continuity? Is it continuous? Is it differentiable? Yeah, it's a nice, smooth, continuous function. So since the endpoints are not included, I'm just going to take the derivative, set it equal to 0, and whatever critical point I get, that is the only possibility for the max. And we'll have to demonstrate that it is the max using the first or second derivative test, and that's it. Okay. So on these, pretty much you know the answer when you take the derivative and set it equal to 0. But they will ask you to explain. So a prime, we're going to call this a prime, is equal to 4 minus 2x. I'm going to set a prime equal to 0. So my critical point is it shouldn't be a surprise to you, that x equals 2 is my critical point. It's a square, yes. Maximum area of a rectangle for a given perimeter will always be a square. Yes, x equals 2. Now, when you start throwing in facts like we're building this rectangular dog pen and we're going to use our wall of our house as one of the sides, then that changes it up. Or if we're going to have this big ranch and we're going to do the fencing on the ranch, trying to maximize the area for grazing, but we have a river over here, then that changes things up a bit. But in general, yes, it's a square. It's a geometry theorem, actually. So x equals 2 is a critical point. So we can use the first or second derivative test. I really like the second derivative test because this is a polynomial. So a double prime is equal to, here's a prime, is negative 2. Okay? Here's what the second derivative test says. We're going to just test 2. A double prime of 2 is going to equal what? If I plug 2 in for x in here, what do I get? Yeah, there is no x in here. It's a constant. So it doesn't matter what the number is. It's going to be negative 2. So since a double prime of 2, the critical point is less than 0, and this is the type of stuff we got to memorize. Well, it's not memorized. Let's, like the discussion we had, let's think about it. If a double prime, if the second derivative is negative, which way is our function opening?
Downward.
Downward. So what does it make sense that 2 would be? Max. Do we have any choice anyways? This is the only critical point. What's it asking for? Max, right? So, yeah. So x equals 2 maximizes the area. Okay. So x equals 2 maximizes the area. And then they might ask you, I don't know if I did here, what is the maximum area? Yep, it does. So what is the largest possible area? So area would equal 2 times 2, or 4. And did I give units on here? Meters. Meters squared. So sometimes they'll ask you, what is the x value that maximizes it? In these optimization problems, they actually do ask for what is the actual value of the max. So they'll ask for the y value, and that's a matter of just plugging it into the original equation. That's it. That's one example. I probably have more examples than we need on this, but we're going to do a couple more that are kind of along the same lines as this, and you'll have plenty of examples to work through these problems here, 1 through 3 and 5 to 9. I really need you to do these between now and Monday. We got to try these before we go on. It's really think about it and try to. So I'm trying to give you lots of examples so that you can do these at home. Okay, so this is, you don't need to necessarily write out this whole problem. Let's just draw the picture. Even in the textbook, they'll do the picture for this for you. So it says a rectangle has its base on the x-axis and its upper two vertices on the parabola 6 minus x squared. Now, the parabola 6 minus x squared has a vertex up here at 6, and if I set 6 minus x squared equal to 0, x squared equals 6, x equals plus or minus root 6. Plus or minus root 6 is somewhere in between 2 and 3. So I know it's going to cross through somewhere down here between 2 and 3. So here's what's happening. This is the picture, and they'll give you a picture even in the textbook on these. And the question is, once again, we've got this rectangle somewhere in here, and there's a certain dimensions for this rectangle. We're going to find what they are. It could be that, it could be something else. But certain dimensions that will maximize the area. Okay. So what is the largest area the rectangle can have, and what are its vertices? So first of all, we need to come up with an equation. Maybe back up a little bit more. Okay, so hopefully you understand we're maximizing the area of the rectangle. Right? We need to get dimensions of the rectangle in terms of just x. Can we do that, you think? Let's call this from here to here x. So what would the whole thing be? 2x. So we've got 2x on the bottom. You with me for this one? You might run into some where they only do half, first quadrant, approximately first quadrant. But this one, it's 2x. And then the height is dependent on the parabola. What's the equation of the parabola? 6 minus x squared. Let me just demonstrate this. If 2 happened to be the right answer, how would I get the height of the rectangle? I would plug 2 in right here. 6 minus 4 would be 2. So it would be 2 and 2 if 2 were x. So the y value, or another way to think about this, the way I think about it is this is x comma y, right? X comma y. And what is y equal to? 6 minus x squared. So it's the coordinates x comma 6 minus x squared. So now I have my dimensions for my rectangle in terms of just x. Can I write an equation? Then I can maximize. So I've got a equals base is 2x, height is 6 minus x squared. And I got a nice polynomial function here. A equals 12x minus 2x cubed. It's a cubic, so it's not quite as nice as the last one, but it's a polynomial function. As a matter of fact, when I take the derivative of it, it's now quadratic, and I can solve it pretty easily. Oh, we should talk about domain. What's the domain here? And it's open once again for the same reason that Jeremiah said the other one was. What's the most I can squish this down to? 0. Yeah, y equals 0. And what's the x values that go with it? Plus or minus root 6. So the domain is negative root 6 to positive root 6. And once again, it's open. I don't need to worry about those because if I plugged in a root 6 or negative root 6, I'd have 0 area. So whatever I get when I set the derivative equal to 0, once again, it's a nice continuous differentiable function, is going to be my answer. So I'm going to know my answer in just a minute here. So a prime is equal to 12 minus 6x squared. 12 minus 6x squared. Set that equal to 0. So x equals plus or minus root 2. Obviously, you can throw out the negative root 2. We could really say the domain here. Let's shorten this. I could just do half that, right? 0 to root 6. I'm trying to find the dimension. In the graph, yes, it's negative root 6 to root 6, but really, in real life, it's 0 to root 6 because I'm finding a positive value x. So just root 2. So x equals root 2 is our critical point here. Call that a CP, a critical point. And man, it's hard to beat second derivative test here. Here's my first derivative. Let's go ahead and take that and get the second derivative over here. So a double prime is equal to negative 12x. So a double prime of root 2 is equal to negative 12 times root 2, or negative 12 root 2. It's a negative number. Since a double prime of root 2 is less than 0, what can we say about root 2? Yeah, root 2 is a max. X equals root 2 is the max. Okay, it's the absolute max, not just the local max. And then I can plug it in. Max area at x equals root 2 is a equals, it was 2 times x, so 2 times root 2 times 6 minus root 2 squared. I'm just plugging that into the original equation I came up with. And what do I get here? 6 minus 2 is 4. 4 times 2 is 8 root 2. So area is 8 root 2 square units. That's it. So that one, just because of the fact that the rectangle was sandwiched in between, was sandwiched inside of the function 6 minus x squared, I ended up with a cubic on them. So the process is the same. I'm going to ask you to do something like this with a cubic on your quiz. Just find it. So you won't have to worry about endpoints, because it's going to go negative infinity to infinity. Okay. It's a nice continuous function, so there won't be any does not exist thing. So the maxes and mins will occur in there. And you could use the second derivative test if you want, or the first derivative. You'll have to end up using the first derivative test anyways, because I'm going to ask you where is it increasing, where is it decreasing. So you're going to have pluses and minuses, intervals of increasing, decreasing. Oh, that's for the vertices? Okay. So areas at, what are the vertices then? Vertices would be at, and let's just talk about the top ones. So you'd have vertices at root 2, comma what? How do you get the y value? Plug it into what? 6 minus x squared. So vertices would be at root 2, 6 minus root 2 squared, or root 2, comma 4. And the other vertex would be at negative root 2, 4. So there it is. I would just worry about that as upper ones. And then you have them also at plus or minus root 2, comma 0. All right, so those are the vertices. All right, I want to do at least one triangle-based line. If we can just do one of these. And then there's a cubic one as well, but I don't know if we'll get to that. If we don't get to that, I'll just take, I think that there's one cubic one on here, a box, and we'll take that one. This may be our last one here. And we'll do the other 3 examples. So it says find the dimensions of a triangle with maximum area. So once again, we're maximizing the area of this triangle. If the hypotenuse is 10. So here's what we have to do. We have to come up with an equation for the area of this triangle that has just x in it, just one variable. And you can do it. The substitution one that's going to come out of this, take a wild guess as to what equation you might use to substitute in to get it turned to one variable. Everybody's favorite from geometry. Yeah, you're right. Pythagoras is going to show up. I'll show you what I mean. First of all, the area formula is only slightly different than the one we've been using. It's a 1/2 base times height. I have neither the base nor the height, but I do have the hypotenuse. And I do know that we can use a and b in here. Let's use different variables instead of x and y. A squared plus b squared equals 10 squared, right? I know that fact. A squared plus b squared equals 10 squared. So this would tell me a squared equals 100 minus b squared, and a equals square root of 100 minus b squared. I'm only going to take the positive square root because we're talking about dimensions here. So if I call this b right here, and this down here a gets replaced with square root of 100 minus b squared. This is the first of my somewhat messy ones. So b times square root of 100 minus b squared. So I use Pythagorean theorem to get my equation in terms of one variable. It will look like this. A equals 1/2 square root of 100 minus b squared times b. And there's any way I can simplify this to make it a little easier, because my derivative on this is a little messier. This is what I was talking about in the square root ones. So you could think of this maybe as a equals 1/2 b, and then this would be 100 minus b squared to the 1/2 power. Are you with me? Get a product rule here. Kind of looks like some of the stuff from chapter 4 test. A little messier, not quite as pretty. But here's the deal: when you have a product rule and you take the derivative and set it equal to 0, you're just going to end up with a proportion to solve every time. And when you have a product rule, you're going to end up with two terms, and you're just going to move one of the terms over and then cross multiply and solve. Okay, to get b. So here we have a prime by the product rule. I always do the derivative of the first. Some of you guys are notice are doing it the way the book quotes it, which is fine. So that'd be 1/2 100 minus b squared to the 1/2. And then it's plus, this one is a chain rule. So we've got plus, I'll write it down here, it's 1/2 100 minus b squared to the negative 1/2 times the derivative of the inner function, which is negative 2b, times the first function, 1/2 b. So that is my entire derivative a prime. And it is going to be easier to write this, I think, to simplify it. When I go to solve it, I want to get it so that it is in fractional form. So I've got 0 equals square root of 100 minus b squared over 2. That's the first term. I'm just changing the 1/2 power back to a square root, and I'm putting that whole thing on the top over the 2. So I'm making one fraction out of it. And this is what you'll do each time with these square root types of functions. And then I have plus, actually it's going to end up being a minus. See that? So we've got a minus sign here. We've got some 2's that cancel. This is a 1/2 b, so that'll be a b squared. That b is actually on the top, it's not on the bottom. So the 2's cancel, there's a negative sign. There's still a 2 on the bottom. So it's minus b squared on the top over 2 times the square root of 100 minus b squared. So this negative 1/2 power, will move that to the bottom. These 2's cancel. These b's, one more time, these b's are both on the top. It's 1/2 b. It looks like the b's down with the 2. It's not. So b squared, so there's a b squared on top. And then all over 2 times that. So those are my two terms, and that'll happen each time with these triangular-based Pythagorean substituted problems, okay? So when I set this equal to 0, I'm going to flop this over to the other side. So I've got b squared over 2 square root of 100 minus b squared equals square root of 100 minus b squared over 2. And that's a proportion. I'm going to solve this by cross multiplying, and it comes out really nicely. Oh, by the way, we didn't talk about the domain on this. What is the domain? How about 0 to 10? Does that make sense? 0 to 10. 10 is the biggest it could be here before you lose area. You no longer have any area. 0. And it's open. So cross multiply here, the radicals get taken out. So we've got, you could take the 2's out if you want to. So we got 100 minus b squared equals b squared. So 100 equals 2b squared. So b squared equals 50. B equals square root of 50. If you want, you could write it as 5 root 2. Doesn't really matter. Square root of 50 is just fine. Although 5 root 2 connects to special right triangles from geometry. Are you surprised that it's 5 root 2? You won't be in just a minute. So the fact that b is 5 root 2 tells me what is a going to be. If you plug 5 root 2 or root 50 in for a, you get, try it. Plug it in and see what happens. I forgot what they asked here. It's been so long. Oh, what's the max area? Okay. So right here, and I really should do the first derivative test. So we've got interval. I'm not going to take a second derivative of that mess. Sine of a prime. So I've got interval goes from 0 to root 50, and then root 50 to 10. And here's what's happening. If I plug in some value between 0 and root 50, oh, maybe 5. If I plug 5 in right here, what kind of sign do I get? Calculations, slightly bigger over there, so it's going to be positive. And then if I plug in something like is 7 big enough? Or let's plug in 9 to be safe. Okay. Yeah. So too hard to multiply 1.2 times 5. But anyways, I think we're okay with 8. But if you plug in 9 here, you'll get negative. It goes from positive to negative. I promise. It's predictable because there's only one critical point. But they will ask you to justify. This is the justification. It goes from positive to negative there. So b equals root 50 is max, and the area is equal to basically 1/2 root 50 times square root of 100 minus b squared minus square root of 50 squared. Anyways, this value right here, this value ends up being root 50 as well. Go figure. It's a 45, 45, 90, half of a square. That's what maximizes it. So it's not surprising. So area equals, that's root 50 times root 50, which is 50. Half of 50 is 25 square units. And we'll stop there. That's a good place to stop. So there's one less problem you'll do. I had them split up 7 and 8, so it's going to be, I'll tell you which one it is. I'll take it out. Let me get that quiz out to you. And I'll take off the one that you don't need to do. All right, here's what we're going to do. Just do, I don't know if this will make any better for A, but long. Just do problem 1 and 2. Just do, not 3 and 4, just 1 and 2. That makes it 10 each, so I promise you, but listen. CB's 10 if you know here. I promise you, you'll be able to show your work and you'll get lots of partial credit. Do just 1 and 2. I think that'll be enough, and then we can start talking about you can start on homework. Some of you will finish in like 15 minutes, but some of you will need a full half hour.
Or some of us will take an hour.
I don't think so, but just do problems 1 and 2. We don't need to worry about 3 and 4. We're going to be hitting on that some more. But man, if you could do 1 and 2, that would be awesome. You can cross the ad. You can rip the whole second page off. You can have the second page. Just as things I expect you to be able to do for the test. So I just rip it off, and we can talk about those as well when I think that's the You do need to know how to do that. But like problem 3 really is all about second semester calculus. And we haven't done a ton of practice of it, but problem 3 is actually pretty easy. But we can talk more about that. We can review it. But do problems 1 and 2. That's it. Rip that second page off. The less I have to grade. There with 10. Or maybe 8 and 12. It'll be 8 and 12. It'll be 8 and 12.
Oh, because
First
there's
one.
4 questions.
First one will be 8 and 6.
I don't know about that.
Don't cry about it till you try it.
Okay. So much be fair there.